So we have an IR spectrum here. On the x-axis, we have wave numbers. Those are proportional to the frequency of these electric waves that travel through the air. So that the higher the wave number, the higher the frequency. It increases as you go to the left, and so waves over here would have a less high frequency, and waves over here would have a much higher frequency. The frequency of the waves is proportional to the energy of the waves. The more frequently the waves hit you, the more energy they're carrying. Kind of like if you were standing in the ocean, the more frequently the water waves hit you, the more energy that water's carrying. So we've got on the x-axis this spectrum, different energies of light that we've shined onto a sample. And on the y-axis we have transmittance, percent transmittance. How much light got through? At 100%, no light would get through. And every time you have a dip, it's a shadow. I'm sorry, at 100%, all the light would get through. It's 100% transmittance. Everything is transmitted through the sample. And then every time you have a dip, you have a shadow. The transmittance gets lower. In other words, less light is transmitted or gets through the sample. And so it casts a shadow. So each of these, you have this sort of line up here. Notice it's not at 100 exactly. That's because the solvent or the machine or something is the air even could be absorbing some amount of the light that you're shining. Maybe it's getting diffracted by molecules in the air, whatever. But you have a sort of line at the top here, and that's your reference point. And from that line, you're going to have dips. And each one of these, all these dips, are shadows being cast by bonds in the molecule. Now every bonds are quantized, so if you think of energy here, increasing as you go up, a bond will have a certain way of vibrating with a certain energy, and the next way it can vibrate will have a certain other energy, and there's no way that it can vibrate in between those two energy levels. When light hits the bond that has the exact amount of energy as it takes to get from this first way of vibrating to the second way of vibrating, then the molecule absorbs the light to vibrate differently, and the light doesn't get through and it casts these shadows. If the light had less energy than that, or more energy than that, the bond wouldn't be able to absorb it, it would just go straight through it. So every bond has a unique difference in energy, a unique difference between the way it's vibrating and the next way it could vibrate. And so every bond will absorb a unique frequency of light, because the frequency of light is related to that energy. So bonds will be characterized by where they show up on this x-axis. There are 9 different types of bonds that you would want to be aware of. And I have them in the table here, and I also have the places where they cast shadows over here. So alkanes, for example, and this is really an sp3 hybridized carbon, so a carbon with all single bonds, to a hydrogen. So it has to have a hydrogen. That bond, the difference between the way it vibrates and the next way it could vibrate, the energy it takes to jump that, is the amount of energy that you get at around just to the right of 3,000 wave numbers. So notice in this spectrum, you have this dip just to the right of 3,000. And that dip is a shadow that's being cast when bonds between sp3 hybridized carbons with all single bonds, and hydrogens bonded to them, starts vibrating in a new way because the difference in energy between the two quantum ways it can vibrate, the two closest quantum ways it can vibrate, has this amount of energy in it. Okay, so that's for alkanes. Oops. For alkenes, if you have an sp2 hybridized carbon, that could bond to a hydrogen. So an sp2 hybridized carbon is one that's involved in just one pi bond. Usually it's in a double bond. That will absorb at 3,100. Now notice each of these little lines at the bottom is 100. So if this is 3,000, this is 3,100 right here. An alkene, if it had a hydrogen to it, would absorb at 3,100. And so likewise, you can do that going down. Just to quickly mention, this alkyne would be an sp hybridized carbon, so that's a carbon with 2 pi bonds to it, to a hydrogen. That's the bond that's going to vibrate, and if that's present, it'll absorb light represented by the energy of a wave number of 3,300. Ketones, and this is a ketone, so an alkane is all single bonds. Alkene, you'd have a double bond. Alkyne, triple bond. Ketones are when you have a carbon double bonded to an oxygen with a carbon on both sides. And this double bond right here in blue, that's the bond that absorbs this frequency of light. For alcohols, alcohols are going to have a smooth, broad absorption between 3,600 and 3,200. So that's what we have here. And here's actually an example of an alcohol, this dip right here. Notice it starts at around 3,600, it ends at around 3,200, and notice how smooth it is. Compare it to this dip right here, which is pointy and jagged. This is smooth and broad. And what's making it smooth and broad are intermolecular forces. So if you have an alcohol, and recall that an alcohol is when you have an oxygen bonded to a hydrogen, and that's on some carbon chain. So if you have 2 alcohols, what can happen? 2 alcohols on different carbon atoms. Remember that capital R is any carbon chain. The oxygens are electronegative and steal electrons for themselves. They become slightly negative. The hydrogens are slightly positive. And so what will happen is the positive hydrogens on one alcohol will start pulling at that oxygen. And the slightly positive hydrogens on the other will pull on the other oxygen, and that weakens this bond. The bond that would be absorbing light. And depending on how many other alcohols you have around, you can form lots and lots of these intermolecular forces. The more intermolecular forces you form, the weaker the bond gets. If the bond gets weaker, then you need a different amount of energy to bump it up to the next quantum way of vibrating. And so what you get is a spread of different different amounts of energy based on the spread of different amounts of intermolecular forces that affect specific alcohol molecules. So 200 to 3,600 is an alcohol, smooth and broad. Next, we have a carboxylic acid. The carboxylic acids have a really broad, smooth dip between 2,200 and 3,600. That's almost a third of the entire graph. It's a really big dip. And that's representing the OH that's in the carboxylic acids. Recall, carboxylic acids are when you have a carbon double bonded to an oxygen and then single bonded to an OH. So this OH here is a lot like the OH in an alcohol. And you'll notice that the absorptions are really similar. But the carboxylic acid is spread out more. It's 2,200 instead of 3,200. And the reason for that is because carboxylic acids can form twice as many hydrogen bonds, twice as many intermolecular forces as an alcohol can. So for example, here you have 2 carboxylic acids, and the oxygens on these are really electronegative, so they're going to be slightly negative. And the hydrogens are losing the electrons because they're bonded to the oxygen, so they're slightly positive. So notice, whereas each alcohol could only form one one hydrogen bond to another molecule, these can pair up and form 2 at the same time. This is called a dimer. But carboxylic acids line up really well to form these intermolecular forces, and it's because they tend to have so many intermolecular forces that the signal gets spread out so much, because you have a huge population of these molecules, And you'll have a spread of one may only have these two intermolecular forces in between, but imagine having similar things like this on top of this molecule and on the bottom, to the left, to the right. The more intermolecular forces you have, the more it weakens this, and the further, the more it would have, more energy the bond would have to absorb to jump up to the next quantum way of vibrating. And so depending on how many intermolecular forces you have, you'll get a spread of how much energy you need to get to the next quantum way of vibrating. Okay, next. You can have esters. Now esters have a very similar absorption to ketones. Esters are when you have a carbon double bonded to an oxygen, single bonded to basically an ether. So an oxygen bonded to another carbon. The absorption is really coming from the double bond to oxygen right here, and we've seen this in ketones already. It's around 1720. I should mention that these numbers here are different in different textbooks. They'll also be different a little bit with every different instrument you use. What these are a rule of thumb. They're a reference you're learning at the very beginning so that you can get a more nuanced appreciation of things later on. It's a place to start. So, 1740, that's about where you'll see the absorption for an ester. Now, a primary amine. An amine is a molecule that has a nitrogen with all single bonds around it. A primary amine, primary is referring to the one carbon that that's bonded to. The other two bonds of the nitrogen are two hydrogens. And because of these two hydrogens that can move together in different ways, you get two dips. So two tiny little points. You'll have like a dip, but that dip will have two little points at the end. And that whole structure will exist between 3350 and 3500 wave numbers. And last but not least, for secondary amines, it's still an amine, so nitrogen with all single bonds around it, but here now it's secondary. That means you have two carbons. And so the last one, you only have one hydrogen, and that's why you only have one dip in the structure here. So we're going to use this to identify different shadows